Great, so last section we'll look at this week is 7.5. As I said before, this section is going to be pretty much not numeric at all. Okay, so you're not really going to need a calculator for crunching numbers or calculating intercepts and roots. It's a totally different section. So we're going to be studying trig identities. Okay, but just as a reminder of what an identity is, it's an equation that's always true. Now, back in algebra, you studied identities. And an identity would come up if I put a problem like this and said solve. Let's say, let's fix that. So if I had a problem like that, I said 2 in parentheses x plus 3 equals 2x plus 5 plus 1. Okay, if I put that on like a Algebra 1 test and said solve, on the left-hand side, you start doing your distributive property. Right-hand side, you combine like terms, and then all of a sudden you have the same thing on the left and on the right. That means this equation is an identity. No matter what value you pick for x, it's always true, because you have the exact same thing on both sides. Okay? We're going to look at identities, basically things that have the exact same thing on both sides, but it's going to be written as trig. Okay, so sometimes it's not always as obvious, like something like this. What's on the left and what's on the right are the exact same thing. We have to just show that they're the same thing. Okay, so it's not as obvious as 2x plus 6 equals 2x plus 6, but it's the same idea. Okay, you should already be familiar with the reciprocal, the tangent, cotangent, and Pythagorean identities. Okay, those are identities that we did back, I think, in chapter 6, and you've been using them every time we have to do something on the graphing calculator with cosecant, secant, and cotangent. Okay. Only way to type those in is 1 divided by. Okay, so I think most people should remember the reciprocal, the tangent and cotangent, also known as quotient. We haven't done as much with them recently, but if you need them again, there they are. So tangent is sine over cosine. Cotangent is cosine over sine. And when we wrote these identities down, there was one last group that I gave you. And in the section when we studied these first, I said, don't worry about the Pythagorean ones. Just write them down for now so you have them in your notes. But we didn't do anything with them. Now we're going to do something with them. Okay, so those are your Pythagorean identities. Okay, these are all on page 403 if you need to go back and copy anything. Also, I want you to keep in mind that you can rearrange these identities. Just like you can take the formula distance equals rate times time, and you could say distance divided by rate equals time. That's not a different formula. It's just the same formula, and you've moved stuff around. Well, I could take sine squared plus cosine squared equals 1. I could subtract sine squared on the left, subtract it on the right, and now I've rearranged it. Cosine squared equals 1 minus sine squared. I'm not going to write down every possible way you can arrange every single identity. That's a lot. But the point is you can move stuff from one side to the other in any of these. So any questions on that idea? All right, so as I said, in calculus, that's where trig identity, this stuff is really used. If, let's say, we don't know these operations yet in calculus, but let's say you had to do a derivative or an integral of this expression as part of a problem. This is going to be a little tough to work with because you've got two separate trig functions and you've got a product between them. If there's a way you can take and simplify all this stuff first, before you do any calculus to it, it's going to be a lot easier to do the calculus stuff. Right? So that's basically what we're going to practice. Just seeing how much can we simplify what we have right there. Okay, and there's a few different tricks we can use Okay, to simplify trig identities. Okay, the first trick is to change everything to sines and cosines. If you go back and look at the chart or table of all the identities I just had up, sine and cosine come up a lot. Every single trig function can be written with just sine and cosine. Tangent can be written as the quotient of sine over cosine. Cotangent, flip it, cosine over sine. Cosecant, you can write with sine. Secant, you can write with cosine. So every trig function can be written with just sines and cosines. So a lot of times when you change to sines and cosines, some stuff cancels out somewhere. All right, so let's try this one. So it says to take the cotangent divided by the cosecant. Notice I don't have any specific numbers here. You don't need specific numbers. Okay, this formula that we're going to come up with, it works for anything. Right, so let's start with cotangent. Can somebody tell me how I could rewrite cotangent just using sines and cosines? Yep.
Cosine divided by sine.
It's cosine divided by sine. And now the bottom is cosecant. How can we rewrite cosecant? Yep.
1 over sine.
It's 1 over sine. And now what you've got right there is basically like this. 2/3 divided by 1/3. You have two fractions and the denominators are the same. So when I see that, I just cancel them. Some people say, well, keep the top the same, multiply by the reciprocal of the bottom, and then they cancel that way. That's the same thing. Right. So denominators are the same, cancels out, and what am I left with? Yeah?
Cosine.
Yeah, I'm left with specifically cosine divided by 1, but it's just divided by 1. So now we took a problem that had multiple trig functions with an operation, division, turned it into a single trig function, no operations in the whole thing. That's much easier to work with than what we had on the left. If we had to do something more with it. In this class, we're done. We don't do anything else. Any questions on that? Very easy to verify, or at least suggest you did this right. Graph your original problem in Y1, graph your answer in Y2. If they look the same, then you probably did it right. But remember, a graph by itself doesn't prove anything. Okay? This algebra that we went through is the proof. Okay, let's try this one. So for the first couple, that trick that I gave you, changing to sines and cosines, will work. That does not work on every problem. Okay, we're going to have to learn some other tricks that we can use. Okay, but let's try the same thing again here. How about cosecant? Devin, how can I rewrite that one? And if you had to graph it, since you don't have a cosecant button, how would you type it in on the calculator?
It would be 1 over cosine.
Careful, 1 over cosine would be SEC.
So 1 over sine.
1 over sine, yes. 1 over sine times, and tangent, Jess?
Sine over cosine.
Sine over cosine. And now we're multiplying, and whenever you're multiplying with fractions, you can always cancel if you have the same thing in the top and bottom. Some people try to do that when we get into problems like this. You absolutely cannot cancel the 3's there. You cannot, when you have an addition or subtraction sign, do not cancel top and bottom. Multiplication, yes, you can. Okay, so sines cancel out. And I'm left with 1 over cosine. And now the tough thing about the direction simplify is how do you know when you're done? Should you stop there? Should you keep going? Well, when I simplify, I would argue if you can write something not as a fraction, that's simpler than having a fraction. So, is there a way we can write 1 over cosine not as a fraction? Secant. So, if you take the cosecant of an angle and multiply it by the tangent of that same angle, that's the same as just doing the secant. Okay. Any questions on that one? All right. Okay, this one's a little different. It says to show that these are not equal. Because sometimes when you start getting into more advanced identities, you don't even know if what you're trying to prove can be done. Okay. First, you have to figure out, all right, is the problem that I'm even getting doable? And then if it is, how do I do it? If it's not, we don't want to waste time even trying to prove something that can't even be proved. So, anyone have a thought on how I could show that these are not equal? Yeah?
Maybe put a cosine under 1 and square both.
So you're trying to think of something algebraically. How do you prove something's not equal? To prove two things are equal, usually you have to do algebra. That's like, or trig. That's what we've been doing. But there's a term. To prove that two things aren't equal, you need a... I don't remember what you need. Yeah?
Inequality?
Not an inequality. It's a term, I think it's probably from, maybe in geometry you learned it. To prove that two things are not equal, all you need is one of these. It's a blank blank.
What does it start with?
The first word starts with a C. Yeah?
Common denominator.
Not common denominator.
What does the second word start with?
E.
E?
CE. You need a CE. You need a counterexample. Okay? To show that two things aren't equal, all you have to do is show that they're not equal once. Because if they're not equal once, that blows the whole idea that they could be equal all the time. Then they're not. Okay? You found one spot where they're not. So how could I show that what's on the left and what's on the right are not equal? Looking for a counterexample. Dan?
Pick a value for theta and just solve.
Yeah, I could just pick a value for theta and solve it. Try to avoid something special like 0, because it might work out that 0 works on both sides. I would do something random like 0.4. Plug in 0.4 radians, or plug in like 37 degrees on the left, plug it in on the right, and see if it comes out the same. I'm going to do what Dan just said, but I'm going to do it graphically. I'm going to look at a picture of the left and the right, and look at a spot where they don't look the same. If they look the same everywhere, then chances are they're equal. Okay? But I'm telling you they're not equal, so they probably won't look the same. All right, so we have 1 plus sine. 1 plus sine squared. And now if I leave it like that, that's exactly how you don't type in sine squared. You've got to put the square on the outside. I just messed up. All right, so 1 plus sine squared divided by cosine squared. Okay, so that's the left, and the right is cosine. I'm just going to do zoom 7. It doesn't really matter what window we look at. We're just kind of seeing, do they look the same? Well, if you know what the graph of cosine looks like, we know it's a wave. It doesn't look anything like that. So we already know these are not equal. But we got to be careful, because remember I told you they might be equal in certain spots? Well, it turns out that if you had plugged in 0 on the left and 0 on the right, you do get the same answer. You get 1 in both. So 0, not a good number to try. But most other numbers, if you try it, it's clear that they are not equal. Okay, so how do you do this? Just find a counterexample. So let's just pick one. Let's do, we're in radians, let's plug in 0.6. So I'm going to call this y1, y2. And if we take and plug in 0.6 into y1, we got 1.94. If we take the same value, plug it into y2, we get 0.83. Therefore, y1 is not equal to y2. We found a specific place where they're not. So.
Should maybe 0.6 next to y2?
Yeah, I don't know why. I think I said y2 and then I wrote 2 or something. Yeah, 0.6. Thank you. Okay, so any questions on that counterexample idea? Really not that hard, also not that as important in this lesson. More important that you understand the kind of stuff in the previous 2 examples.
So would we only write like one example?
Yeah, you only need one spot. Yep. It's like if somebody says I tell the truth like all the time, and you can think of one time that they didn't. Well, then that proves they don't tell the truth all the time. If you can just think of one time that they didn't. Same thing here. Just find one example where it doesn't work. They're not equal all of the time. Okay. All right. What's nice about verify versus simplify, when you have a verify problem, they basically give you both sides. They're telling you what to start with. They're telling you the answer you're going to get. All you have to do is figure out how to get there. Okay. With simplify, it's kind of open-ended. You don't know where you're supposed to end up. So you just have to keep going until you think you're done. Okay, so whenever you have a verify, you always want to start with the side that is more complicated. Most of the time when you see the directions verify, one side is going to look more complicated, the other side is going to look simpler. So if I go back to the question I just showed you, I think it's pretty clear in this problem which side is more complicated, which side is simpler. It's a lot easier to take something that's complicated and simplify it, rather than take something that's already simplified and try to complicate it. That's kind of hard to do. If you have a problem where you really can't decide which side looks more complicated, then start with either side. But most of the time it's going to be pretty clear which side is more complicated. Another approach, but people usually get messed up with it, is they try to simplify both sides at the same time. I'm going to say stick with one side. Just stick with one side at a time. Don't mess with the other side. Okay, so a second trick we can use, besides writing everything in terms of sines and cosines, is to find a common denominator. So just like with numbers, if you had 2/3 plus 4/5, one way to find a common denominator is to multiply each fraction by the other denominator. So, could multiply the fraction on the left by 5/5. Multiply the fraction on the right by 3/3. And there gives you a common denominator of 15. We're going to do the same thing with trig. When we first look at that problem, it doesn't look like there's going to be anything to do with common denominators. There's no fractions in the whole thing right now. But as we go through it, we're going to create fractions just by the work that we do. All right. What property do you think we could use here that we use in algebra all the time with numbers and letters? Yeah?
Is it distributive?
Yeah, distributive. Whether you want to change things to sines and cosines first and then distribute, or distribute and then change it, it doesn't matter. You've got to do both. I would distribute first. So you've got sine times cotangent plus sine times tangent. Now the second trick doesn't apply yet. There's no fractions in the problem. Let's change everything to sines and cosines and then see what happens. So sine, it's already sine, but since I'm going to be making everything into fractions, I'll put it over 1. Okay. Cotangent. What is cotangent?
1 over tangent.
You can do it as 1 over tangent, and there's actually a problem at the end that I'm going to do where it is helpful to change everything to tangents. I'm not saying it wouldn't work, but it's going to be easier to change things to sines and cosines.
Cosine over sine.
Yeah. How do you know what works and what doesn't? Like if you have multiple ways you could do something? Well, it's kind of like doing a Sudoku and you're trying to figure out what number is supposed to go in the spot and 2 numbers could work. It's just practice. And if you find that you get later on in the problem and it's getting really hard, you probably made a mistake where you guessed which way to go about solving it. So take a step back and try something different. All right. Sine over 1. And what about tangent? Scott?
Sine over cosine.
Sine over cosine. Now, I've got, if you look at the second fraction, if you look at this one, can I cancel the signs out?
No.
No, why not?
Because it's addition.
Absolutely, it's across a plus sign. You can never cancel across a plus sign, but you can cancel across a product. Unfortunately, nothing else cancels in the other one. So now that's going to lead us to having some fractions. So we have cosine over 1 plus, what's sine times sine? Sine squared. Just like x times x versus x plus x. We have to keep that straight. 1 squared, 1's doubled. Okay, this is sine squared. Okay, so now we've already used the first trick, change to sines and cosines. So you can't do that again, it already is done. So what could I do with this? Yep, Abby? Yeah, let's find a common denominator. And can you tell me what my common denominator would be, Abby? Cosine. The common denominator is always the product of the 2 denominators that you have. Now, since the fraction on the right already had the common denominator, you don't have to do anything to it. The fraction on the left doesn't. So what do I have to multiply top and bottom by to make the fraction on the left have the common denominator? Yep. Cosine. So cosine and cosine. Don't even worry if you don't understand where the problem is going. Just do the steps and then hopefully if you do them right, something is going to happen every time. Okay. But after you do enough of these, you kind of already know ahead of time what is going to end up happening. But it takes a lot of practice to get to that point. Okay. So now we've got cosine squared plus sine squared over cosine. Okay, so we've done the sines and cosines, we've written it with a common denominator, so now there's got to be something there that simplifies. Does anyone see something there? Yeah?
The top simplifies to 1.
The top all turns into 1. Okay, it's this identity. It's rewritten a little bit. It's cosine squared plus sine squared, but that equals 1. So now we can cross the entire top out and make it 1. And lastly, 1 over cosine, that's a reciprocal identity, it's secant. So given what we started with, we had 3 different trig functions with a distributive property and a sum. And after simplifying the whole thing, the distributive is gone, the sum is gone, all 3 trig functions are gone, we're down to 1 function. Much, much simpler to work with. Any questions on that? Now again, you could double check This doesn't prove anything, but you could put secant in y1, you could put the original problem in y2, and you could check and see, do the graphs look the same? Now, just because they look the same, that doesn't prove you did it right. But if they look the same, you probably did it right. Okay. But remember, a graph by itself can never be used to prove an identity. You have to do this to prove an identity. Questions on that? Okay, so that's more of a middle difficulty. I'd say the first two were kind of easy. This one was more middle. Okay, it had a lot of different stuff in it. Okay, let's look at this one, verify. Okay. Again, nice thing about verify is you already know the answer. The answer is sine. So when you get sine, you're done. So we're going to start with the right-hand side, and we're just going to keep playing with it until we finally turn it into sine. I'm just going to copy it down so I've got some space to work. Okay, any suggestions what I try first? Yeah?
Change everything to sine and cosine.
Yeah, why don't we change to sines and cosines? If you were thinking common denominator, you can't. You already have a common denominator. Common denominator means you have two separate fractions. You only have one fraction here. Okay, so let's just change to sines and cosines. And then maybe common denominator will pop up. So secant is 1 over cosine. Tangent is sine over cosine. And cotangent is cosine over sine. Now, if we look at the bottom, can I just cancel everything out? Sine in the top, sine in the bottom, cosine top, cosine bottom? No, that's addition. If that was multiplication, that'd be great. Everything would be gone, and it would turn into a 1. Now, if you look at what we started with and what we have now, I think what we have now actually looks worse. Because now we have fractions over fractions, but that usually happens. Okay, as you start to simplify, it's going to look worse before it starts to look better. In the top, there's not really much I can do. It's just a fraction by itself. But in the bottom, there is something I can do now. Anyone see what I can do? Just focusing on the bottom. Yep.
Common denominator.
Yep, find a common denominator. So we're just going to keep copying the top of this fraction down for pretty much the rest of the problem. So let's find a common denominator. Common denominator, it's the product of the two that we have. We have a cosine and a sine. So common denominator, cosine, sine. Okay. What is the fraction on the left missing so that it has the common denominator?
Sine.
It's missing sine. So we're going to multiply by sine over sine. What's the fraction on the right missing? Yep. Yeah. Cosine. Cosine over cosine. And now if we multiply what we have in the left part, Tyler, what's sine times sine?
Squared.
Sine squared. And what about the other part?
Cosine squared.
Cosine squared. And we just used this Pythagorean identity earlier. What's sine squared plus cosine squared? 1. Now we're finally getting to something that is starting to look a little better. So we have 1 over cosine divided by 1 over cosine sine. Okay. Fraction divided by a fraction. A couple ways you can think about it. You can just take with the top, keep it the same, and then multiply by the what of the bottom? Reciprocal. So the reciprocal of the bottom is cosine times sine. 1. And now what can I do there? Yep,
Cancel out the cosines.
yep. Cancel those. And what am I left with?
Sine.
Sine. Which we know we're done because that's what the problem originally said it was supposed to equal. So that's a verify. Any questions on it? Okay. All right, so the third trick, okay, these aren't the only tricks you use with trig identities. These are just ones that are very common. Okay? But a third trick you can try is multiplying by the conjugate. So remember when we did imaginary numbers? If you had 2 plus I, what was the conjugate of 2 plus I? Anyone remember? Yep.
2 minus I.
2 minus I. Now, we're not doing imaginary numbers. I'm just showing you that conjugates are used in other places besides what we're doing right now. So 2 plus I, 2 minus I. So what's nice is it's very obvious when to use this trick. You're going to have a trig function, plus or minus, and then a number. When I look at that, I think conjugate right away. 1 plus sign, 1 minus sign. Okay, think about the bottom. You wouldn't use conjugate in this problem. It's not a trig function, plus or minus a number. Same thing here. It's not a trig function, plus or minus a number. If we go ahead one, that's another one where you definitely use a conjugate. It's a trig function, plus or minus a number. Doesn't matter if it's in the top or in the bottom. Conjugate. We'll finish up with that one last. Okay, so let's look at this one. So it's a verify. So we know one side is what you should start with, one side is what you should finish with. Which side looks more complicated here? Dan? How come? Because you're subtracting. Well, how about on the right side though? You're adding sign to 1. Any other thoughts? Yeah?
I'd say left side only because you could possibly get a like a negative number from 1, or not a negative number, but you can get. It would be harder to subtract something from 1 than to just add 1 to it.
It's harder to subtract something, so you're just thinking maybe subtraction is a harder operation than addition.
The way it's set up.
The way it's set up there. Okay. With this one, I mean, you could kind of make a couple different arguments, but really you've got a denominator on one side that has a number and a trig term, and then you have a numerator on the other side that has a number and a trig term. You've got a denominator on one side that's all by itself. You've got a numerator on one side that's just a single term all by itself. So really, in this one, I don't think it's as clear as it is in this one. Which side is more complicated? Okay. Each side has the same number of operations. Each side has exactly the same functions. It's just the difference between one side has a plus, one side has a minus. So they're pretty similar. And because of that, you could start with either side. So do we want to start with the left side or the right side? About Meili, what do you? I'll let you decide. The left. Oh, that's okay. We can do it. So we'll start with the left side, and our goal is to turn it into the right side. Whichever side you pick, it's going to be exactly the same steps in exactly the same order. Very, very similar. Okay. So let's take the left. And in my head, I'm running through all the tricks. Change to sines and cosines? Nope, it already is. Find a common denominator? Nope, I only have one fraction that I'm working with. So the only trick I have left is to try the conjugate. What's the conjugate of 1 minus sine? 1 plus sine. 1 plus sine. 1 plus sine. Whether you use t as the variable or theta as the variable, that doesn't affect anything at all. You can use whatever variable you want. Now, whenever you have a problem like this, you have to use FOIL, distribute it all out. But I'm going to start with the bottom. Anytime you have conjugates, always multiply them together. Bless you. Because you're going to get something to cancel. So start with 1 times 1. But now don't write down the next step. Just watch what happens first. 1 times positive sign, 1 times negative sign. What happens there? Yeah? It cancels out. So with conjugates, you don't have to worry about the outer and the inner. Just the first and the last. Negative times positive would give me a negative sine squared. Now, the reason I did that first is because I see 1 minus sine squared. And if I go back to this, I remember doing that earlier. 1 minus sine squared is a trig identity rearranged. Okay? It's going to turn into something. So now that I'm thinking that's going to happen, I'm not going to distribute out what's in the top, because I already know what the bottom is going to be. I'm already seeing something similar to it in the top, so it's going to end up canceling. And that's a little tricky. Okay, how would you know that? It's kind of like if you play chess. Okay, the whole idea with chess is you're trying to figure out what's going to happen or what your opponent's going to do, like 2 or 3 moves ahead of where you are now. And the only way you figure that out is practice. So that's what I'm doing here. Kind of trying to figure out what's going to happen 2 or 3 steps from now. But that's not very easy to do at first. So keep the top exactly the same. Cosine, 1 plus sine. If you made a mistake and you distributed out the cosine, you can still solve the problem. It's just most people, they may end up making more work for themselves, and because there's more work, they usually mess up the next step. Okay. So, all right. So now, 1 minus sine squared, we just looked at an identity. That was cosine squared. So we have a cosine squared at the bottom. We have cosine, 1 plus sine at the top. What do the top and bottom both have in common now? Cosine? How many? Just 1. There's 2 in the bottom, there's 1 in the top. That means you can cancel 1 from everything. 1, 1, and look what you're left with. 1 plus sine over cosine, 1 plus sine over cosine. That's exactly what we're supposed to get. So this type of problem, where you've got a single trig function in the top, and then in the bottom, or the top, depending on which side you start with, looks like this. This is the exact same thing we just did. You're going to multiply by a conjugate, you're going to FOIL it, something's going to cancel, and you're going to get a Pythagorean identity, which is then going to cancel something else. And that's going to be the whole problem. Okay. So, any questions on this one? Okay, so what I'm trying to do is just show you every kind of thing that can come up. And at this point, I've pretty much shown you all the different things that can come up for the kind of identities I'm going to give you. Okay. In general, identities can get really hard. Okay, there's been some, like Mr. Babs brought to me from calculus, and it's taken us a while to figure it out. Some of them are just, if you're not thinking of the right trick to use in your head, you end up making the problem way worse than it has to be. And a good example of that is this one. Again, which side is more complicated? I would argue the right, only because the right has 4 things. It has a tangent, a cotangent, another cotangent. The left side only has 3. But then you might say, well, the left side has things that are squared and the right side doesn't. So, really, you could start with either side. But let's start with the right. Any thoughts about what I could do on the right-hand side first? Think about all the tricks we learned. Yeah?
Change to sine cosine.
So that might be what you'd think first, right? Change everything to sines and cosines. And you absolutely can get the answer doing it that way. Okay? There's always a way to get the answer, no matter how you start. Just how difficult is it going to be? That turns out to be kind of difficult. So in this problem, this is kind of an exception to changing everything to sines and cosines. Let's change everything to tangents. Okay? Something we haven't done before, but it is something that just works out really, really nice. So let's rewrite this. How do you write cotangent in terms of tangent? Yeah? 1 over tangent. And then the bottom is the same thing, just change the minus to a plus. These are kind of like conjugates. We normally do conjugates with a number, but it's kind of the same idea. Now, if I look at the left-hand side, and that's what I want to get, and I look at what I have, I'm trying to think of a way, how can I force what I have to look like that? And I just do it like a term at a time. Look at this. You have to turn it into that. How could you turn tangent into tangent squared? Multiply it by tangent. Now, if you multiply that by tangent, you can't just do it there. You have to do it here, here, and here. And let's hope that by doing it everywhere, something nice ends up happening. Okay, let's multiply top by tangent and the bottom by tangent. Just tangent, not tangent squared. Okay. Tangent times tangent, that's good. Tangent squared. What's tangent times 1 over tangent? 1. We just got the other number that we wanted in the top. Perfect. Now let's do the bottom. Tangent times tangent. Tangent squared. And then again, tangent times 1 over tangent. 1. Now that's not what we want in the bottom. But does anyone recognize the top is good, so I wouldn't mess around with that anymore. What about tangent squared plus 1? It's secant squared. At this point, all you have to do is recognize this identity. 1 plus tangent squared is secant squared. You don't have to prove why that's true. But that's an identity. You can just work with it. Okay, so let's go back to what we had. So tangent squared plus 1, 1 plus tangent squared, that's the same thing. Turns the bottom into secant squared. And the top, tangent squared minus 1, and we're done. So really, I would argue in this problem it was 3 steps. Change to tangents. Multiply top and bottom by tangent. That step was a little tricky to come up with. And then the third step was a Pythagorean identity. In another pre-calc class, we did try changing to sines and cosines. And off the top of my head, I ended up getting stuck. We had gone at it for about 4 or 5 minutes, and then we got to a point where I wasn't sure where to go from there that was helpful. So we tried this approach, and it's much cleaner, very quick. But that's the problem with these. You just have to think of the right trick. So if you get on a problem and it's not working out, and it's seeming like it's really hard, take a step back and just try a new approach. Okay, try something different. Okay, any questions on that one? All right, so I think you've got a bunch of different examples that you can look at for reference. This one I'm not going to go through, but this would be a good idea if you were in calculus and Mr. Babb gave you a problem that said, I want you to prove that if you can. I'm not giving you problems that say prove if you can. Okay? But if you don't even know whether or not what's on the left and what's on the right are the same, one approach is to graph them first. If they look the same as a graph, they probably are the same. And you can probably prove it somehow. But if you graph it and they look totally different, don't waste your time trying to prove it. Just say that they can't be proven and give a counterexample, and you're done. Okay? So remember, graphing calculator, all it can do is support the idea that two things are equal. It doesn't prove anything. You have to do all the algebra to prove something. I'll skip over that one for now. I have a bunch of them, but I think you've seen enough of them. All right, so I'm going to give you two worksheets. Okay, so the first one is the homework. That's the review worksheet for the test. The second worksheet I'm going to give you is just a bunch of trig identities to practice. I'm going to email you a link that has all the answers. I think it's, like I said, 16 minutes, and I go through all 10 problems. So if you want extra practice for trig identities for the test, you have this, and you can look up all the answers so you'll know what you're doing right or wrong. Test tomorrow on Friday. Okay, I will be after school today if anybody needs to come by for extra help.